Hello everyone. Today we are going to introduce an important service in Azure related to the machine learning and AI in general. So this session, we can consider it as introductory session for Azure machine learning. Before diving in the Azure machine learning service itself, let's have an introduction about the machine learning in general, just to understand what we are talking about, what kind of problems we try to solve here. And let's switch to the presentation for today. In today's session, I'm going to divide my talk to two sections. Mainly the presentation that we are going to introduce the theory or the theoretical part of the story, but most of the time we are going to focus on the implementation and exploring the Azure machine learning from Azure portal itself, as well as from programmatic point of view. If you are coming from development background, I think you'll be happy to see this kind of implementation in using code. So we have different approaches to work with Azure machine learning. We are going to actually cover like 2 or 3 demos today, just to make sure that we can interact with Azure machine learning service from different ways, either from Azure portal or from the SDK using Python. So let's start with the introduction to machine learning. In my presentation here, we have the introduction to machine learning. Machine learning mainly is a branch of the AI, of the artificial intelligence, and the focus of machine learning is to learn from data. We have data, and we are trying to solve problems with data in hand. We are trying to improve the accuracy over time without actually having explicit programming based on specific predefined rules. So this is the main idea. If you look into the picture here, it's actually summarizing the relationship between the artificial intelligence, machine learning, deep learning. So you can see obviously here that machine learning is a subset of artificial intelligence, and also deep learning is a branch under the machine learning science. This is actually the basic categorization when it comes to how machine learning and deep learning reside in the ecosystem of the artificial intelligence. We have different types in machine learning. So we have supervised learning, we have unsupervised, we have reinforcement. What is the differences here? In the supervised learning, we actually have features or variables which actually could be mapped to labels. So we have a data like some information about diabetes. We have some information collected from diabetic persons, and this information actually, as a result, we can, based on the historical records, we can find a mapping between this information and how much percentage of diabetic level this person is, or maybe based on these inputs we can decide if this person actually is diabetic or not. So this kind of data, which we have it as a labeled data. Labeled here means that it has a specific outcome, and we can map the inputs to this specific outcome. In the supervised machine learning, it comes actually in 2 flavors. It comes as a classification problem or as a regression problem. The classification problem means that we have the inputs in our data, and these inputs will be mapped eventually to outcome, and this outcome could be a discrete value, yes or no, a patient or not patient, his income is above a specific level or under this level. If we have, for example, as a real example for classification, we have the input here is an X-ray for the patient, and based on X-ray, we need to train a machine learning model to predict if this patient has pneumonia or not. this is a kind of classification, because eventually we have a lot of data for other patients we collected over time, and we trained our machine learning model to find a proper mapping between the inputs, which is the X-ray in this case, and if this diagnosis based on the X-ray is has pneumonia or not. So this is yes or no, or binary classification problem. We call it binary because the outcome here could be yes or no, patient or not, has pneumonia or not. On the other side, we have the second flavor of the supervised machine learning, which is regression problem, which is like, for example, we have some inputs about a specific house prices, and we can find some features about those houses and map the features of the houses based on different dimensions to the price of this house. So the outcome is a continuous value. It's not a very discrete value here. So it could be any number, any real number. That's why we call it regression, because at the end, we are going to predict a continuous number, a real number, which is the price, which may be the stock price tomorrow based on the historical value for this specific stock, and so on. So this is the kind of problems which we have it under the umbrella of the supervised machine learning. The second type is unsupervised machine learning, which is mainly unlabeled data. We have data, but this data is not labeled with a specific outcome or a specific output. So we have general data, and from this data, which is unlabeled, as we said, we need to find some insights, some hidden insights about the data. For example, the customer segmentation. We have some data about customers. There is no specific label for those customers, but from this historical data, we want to make a segmentation for those customers to see if those customer has a similarity between their purchase style or purchase behavior, and so on. One famous example as a real scenario for the unsupervised learning, if we switch here to Google News, for example. Let me share the screen here. We can see here that this is Google News. And in Google News, this is a kind of clustering, because see, you have here the news, and those news has been actually clustered together based on the similarity between the different items. So how this actually has been implemented, it's a kind of clustering, because these items or these different news has been clustered as a story, which has a big similarity between each other. That's why we have it here together in this story about a specific topic or related topic, okay? So this is a kind also of real similarity, real use case for the unsupervised machine learning. As we said, this is a clustering problem. If we switch back here to the presentation, finally we have the reinforcement learning. Simply in the reinforcement learning, we have a software agent, and this agent lives in a specific environment, in a specific context. And we want this agent to learn in adaptive manner, how to interact with the surrounding environment. We specify specific predefined gain for this agent, and based on this gain, the agent tries to maximize the gain. So what the agent is getting from its context or its environment, information about or feedback about its behavior. So if the agent did a specific action, and this action caused a specific gain, the agent will be receiving a feedback that, okay, this is the gain that you get, or this is the losses that you get, and based on that, by time, the agent in an adaptive manner will learn how to maximize its gain over time. So this is a kind of a problem where we have a specific objective to maximize the gain of specific actions or a sequence of actions, And the agent, based on this general rules of maximizing the gain, can adapt its behavior to eventually achieve the final objective, which actually very obvious here as a use case is the self-driving cars. In the self-driving cars, we have this kind of implementation for reinforcement learning, okay? What you see here as a sub-items is different flavor or different subcategory under each type, like classification, regression, clustering, and under reinforcement, we have something called Q-learning or a deep adversarial network, and so on, okay? So this is the main types of machine learning. Moving on, we can see here that, as we said, this is a supervised learning. We have very specific data that could be actually classified based on a specific outcome, or the unsupervised, because we don't have here any labels for the data. That's why, based on the similarity, we start here under the unsupervised, grouping the points or grouping the customers in this case based on the features that we have about their historical data or their purchase behavior or something like that. On the right side here, we have cloud of points. Each point here represent maybe in reality a customer, okay? And this customer or this, as we said before, X-ray as an input, or we have an image to classify, either it's cat or dog. And finally, we need to find a separator. You see this line we call it a decision boundary, and this decision boundary will make the right classification between the red points and the blue points. This red points could be cat, and this blue points could be a dog. Later on, when we have the model trained well on the trained data set, we are going to use the same model to predict unseen data to see, okay, a new image which has not been seen before by the model. Is it cat or dog? Is it pneumonia from the X-ray or not? And so on, okay? So this is also on the right side what we have here in the graph showing a classification problem. Here in the regression, we have these cloud of points, and these could be each point could be a house with its features. So each point represents an instance, and this instance in the data represent a house, for example, with multiple features about the house. Based on these features, we can fit this red line to the data, and eventually after doing the training of our regression model, this line will be representing our model. So later on, if we have a new data about new houses and we want to see or to predict what is the proper price for this house given these features, finally the model will be able actually to generalize and produce the right predictions with good accuracy based on what the model has been trained on. So this is the main idea, and eventually here we have the clustering. As you can see on the left side, we have the original unclustered data. It's completely unlabeled data, but we was able on the right side to cluster this data based on the similarity between the different points. And instead of having everything seamless on the left side, we was able to cluster the data to three groups. So we have the green group, we have the blue group, and the red group. These three groups actually represent the similarity between each group. So based on this, we expect that in the underlying data, there are some insights that we was able to figure out in this data to say eventually that, okay, this there are similarity between these specific points in the green group or the green cluster, and there are similarity also in the blue points, and another similarity aspects related to the third cluster of the red points. Okay, so this could be, by the way, as we said, cluster segmentation, or could be a group of documents that we are clustering or grouping based on the similarity of the topics introduced in these documents or these news, and so on. Here we have the workflow for the machine learning. This is the typical workflow for the machine learning. And actually, this is very important. Why? Because I want you to understand the high level, the big idea. And later on, when we dive into the Azure machine learning service and the machine learning workspace, we will try to simulate this big picture or the big idea in this typical workflow of the machine learning to what we have under the machine learning workspace, how to achieve each phase or each stage of this workflow. So if you look here, you start from the left side with the data preparation or data pre-processing, where we have the raw data and we are trying to make some kind of transformation on the data to make it ready for the training as a second stage. This pre-processing on the raw data could actually include cleansing the data. So if we have like missing values, or we have null values, or we have some columns with too much nulls or none values and so on, we might have outliers. And these outliers represent noise in the data set that we want to make sure that it will be excluded before doing the training on this data, because these outliers can make a big impact on the final trained model, because we look into these outliers as extreme points, which might be an error in the collected data. That's why we need to make sure to remove these outliers before going further in the pipeline. So this is the data pre-processing part. Moving on to the second stage, we have the train model. This is the main stage which everyone starting in the machine learning field is focusing on, because in this is the most exciting part. However, if we look back to the first stage of data pre-processing, sometimes we have 80% of the time we spent on the data pre-processing phase. But in the train model, we have the cleansed data, and we are trying actually to train the selected model. We have algorithm, like we have a classification problem. So we decided to work with a random forest algorithm or logistic regression algorithm. And this kind of algorithms we are going to use to fit our model to the pre-processed data. So this is the process of training the model. We are fitting the model to the given data, and finally the model during the training will try to find the proper mapping between the inputs and the outputs, because as we said before, the classification and regression is a kind of the supervised machine learning problems, which mean that it's a labeled data. It has already a specific outcome in the trained data set, okay? Once we have the trained model, we get it as an artifact, and we are trying to package this model in a specific format. What kind of package we can get? We can get this in a different formats, actually, like Becker files, or this is a specific format that we can serialize our model into. So later on, we can make our model, our trained model, in a serializable state or a portable state. So we can move it from experiment to another, or to actually use it for inference or making predictions in a different environment. So this is the packaging part. Moving on to the fourth stage, it's the validation of the model. Validation of the model means that we want to make sure that our model can generalize well in the real world. If the main purpose of this model, for example, was to detect a specific disease, we want to make sure that if we expose a new data to this trained model that the model didn't see before, the model will be able to recognize well with a good accuracy or high accuracy the disease, can classify the disease, or can classify, for example, the image if we are talking about computer vision problem. So this is the kind of validation we want to make before allowing the public users to make use of our model. If we are talking specifically about disease identification or cancer classification, for example, to make sure is this benign tumor or something else, Our public users here will be doctors, and those specialized doctor eventually will use our model to, in practice or in the real world, for a new patients to identify if this person has a kind of benign tumor or not, and so on. So this kind of validation, it's a testing for our model. And finally, if we are satisfied with the result and the final outcome, we can move to deploying our model to our target audience, our actual users. While deploying this model to the production, we have to keep monitoring the model, which is the last stage, because over time, the data itself is changing, and the pattern and the distribution of the data could change. This change in the data could lead actually to a degradation in the performance of our model and cause something we call it data drift, okay? And this initial performance that we was happy with at the beginning when we deployed our model in the first stage, after a while it will be maybe a bad performance or a kind of performance degradation that this specific business cannot afford, and so on, okay? So this is the monitor model, which means that we keep an eye on the model in production to make sure that it's still doing well. It's still doing as expected. And if some drift happened in the data and the model performance, we have to make sure that we are going to have a proper pipeline to retrain again the model against the new data, the new distribution of the data, and ship the new model to the production again to make sure that we are maintaining the performance well. This is actually the same thing, but with some more information about that. This raw data could be actually split into testing data and training data. The training data, this is a kind of data that we are exposing to our algorithm during the training phase. And this is the validation part that we have seen in the previous slide. And the testing data, as you can see, it's something we hide from the algorithm and from the model during the training. We only expose the testing data, which part of the raw data, to make sure while doing the validation and testing of the model that this model still can generalize well for the unseen data, which here in the testing data set. And finally, this model will be in production in the fifth box here. And this model, while it's in production, it receives new data from the bottom and actually generate predictions based on the given data. Okay. Now let's move on. I think this is a good introduction about machine learning in general for the beginners. And if we move on actually to the Azure related topics, we have, when we start with Azure machine learning, we start from the machine learning workspace. This machine learning workspace is the top level resource. It's an Azure resource, and this resource, it's an Azure resource like any other resource we are creating in Azure, from Azure Portal or from Azure CLI. And this Azure resource is actually encapsulating all the other underlying resources to serve the needs of the machine learning. So we have the top level resource, which we call it Azure Machine Learning Workspace. And inside this workspace, we have a lot of things we can do, but from the workspace itself. So even if we are creating compute resources for the machine learning purpose, if we are make any actually provisioning for any other resources like ACR, Azure Container Registry, to host specific Docker images or container images inside, because it's a part of a specific machine learning experiment, this is also managed centrally from this top level resource, from Azure Machine Learning Workspace. So as you can see, the description is clear, providing a centralized place to work with all the artifacts. I try to give example about what kind of artifacts we might have. This is the kind of artifacts we might have, and we are going to see this in the demo while exploring the Azure Machine Learning Workspace, okay? Here in this slide, we can see that when we create an Azure Machine Learning workspace, by default, there are some other resources created for us by default, actually, because it's needed. The machine learning workspace is something big, and it has a multi-purpose things. That's why we have at the top here, you can notice that once you create a machine learning workspace, you will find that by default, there is an Azure storage account created to host the artifacts, logs, and all the data related to this specific workspace. We have also Azure Key Vault to store the sensitive data about our experiments, about our computes related to this workspace. And we have Azure Application Insights to make proper monitoring on what's happening inside this workspace. And finally, we have Azure Container Registry created, but keep in mind that for Azure Container Registry, it's not created by default. It's your choice. You can choose to create it while creating the workspace from the portal. However, by default, it's not created. But once you have a need for hosting Docker images, either for training purpose or for inference purpose, these kind of images automatically will be pushed to a newly created ACR, a newly created Azure Container Registry. And at that moment, when you need it, it will be provisioned automatically for you, just to make sure that the cost is optimized and you don't have any extra cost without any need. But as I said, you still have the choice to go and change this default option and create it while creating the workspace itself. In the workspace, once you are launching the workspace, as we see after a while, you have actually assets. In the bottom here, we see assets, and these assets actually could be environments. These environments is a container for what prerequisites you need to run a specific experiment in machine learning workspace. The experiment itself, what is the experiment? Experiment means actually it's an analogy to what is the machine learning is all about. Machine learning as a science, by nature, it's experimental. It's experimental science. It's the trials. We are doing many trials. We are tuning many parameters. We are trying to find out and solve a specific optimization problem. That's why it's a very good thing to have this kind of terminology, which is a real analogy for what is the machine learning science is all about. So this experiment is a collection or a boundary for multiple trials or multiple runs of a specific machine learning problem. So if we have a classification problem we are trying to solve, we are designing this experiment, and once we have the pipeline, which is actually train the data and train a model to solve this problem, we are running this specific pipeline many times, and each run or each trial, it's actually a child under the experiment. It's a container. The experiment is a container. We will see this in a very practical way in the demo. And the pipeline is sequential stages or sequential activities, like what we explained in our typical workflow of the machine learning. Because if you notice, this is the kind of pipeline we are talking about. We start from the data pre-processing, moving on to the training of the machine learning model, validating the model, moving the model to production. This is the kind of pipelines. And in Azure Machine Learning, we have two types of pipeline. We have training pipeline, where we are concerned about the training phase of our machine learning model. And we have inference pipeline, where we are using the trained model to serve predictions, to produce predictions, and actually to do the job that this trained model should do for the public users or for a specific target audience. And we have also the data sets. These data sets is our data that we are using as an input for any experiment in the machine learning workspace. And we have models. The models is the output or the final artifact after the training phase is done. And we have endpoints. The endpoints is the deployment or the deployed service that we can consume from the client side to serve a prediction, to produce predictions from our model. So this endpoint, literally, it's a REST endpoint, REST API endpoint, a web service that we can consume it from a mobile app or from a web application, or even from, if we want to test as developers, we can open Postman or assemble command prompt to make sure that we can make a query request, for example, web request against this specific endpoint, as we will see after a while. So this is the main assets that we have here in this slide. On the left side, on the right side, we can see that managed resources, and this managed resources is all about compute. And we have also the something called, when we talk about compute, actually, before moving on, the compute here, because there is a fact. We have a model, we try to train on a data, and we have to pre-process the data, make a lot of activities in our pipeline, as we said. So these kind of activities needs a compute at the end. This compute could be a cluster of nodes, could be a VM, could be a GPU-enabled machine, could be a big cluster or a big AKS cluster, Azure Kubernetes service, because we have a huge amount of data. Could be even Databricks cluster if we have too much data, a big amount of data, and we have in each stage within our pipeline, we have to make huge, huge computation on this data, and the training itself could be a computer vision problem, which is trained on video frames or images or any kind of media data, which is by nature, it's big, or if we are talking about computer vision, which is related to the deep learning branch, it's by nature needs too much data to have a proper accuracy for your trained model. So at the end, as a conclusion here, all the time while experimenting in your workspace, you need compute resources. And these compute resources could be for the training purpose or for the inference, for producing the final outcomes of the trained model. That's why we have the compute here as a very important part of the ecosystem. We have also something called the data stores. Please, here it's mentioned linked service. Don't confuse it with what you will see later in the workspace under the same title, because there is a recent service has been released in the workspace recently called the linked service to link the workspace to external service in Azure, like Azure Synapse or something like that. But actually, this is something different here. Forget about this linked service word, as it might confuse you with what we have in the workspace. But what we mean here, that it's a linked service in the sense of it's dealing with external resources, because the data store here is a terminology where, or representing abstraction for the storage solution this workspace is using. If you remember, we said we have to provision by default the workspace. Once created, it's provisioning Azure Storage account. And this Azure Storage account actually is the underlying storage solution that we are using by default. But in the workspace itself, we have a kind of abstraction between the Azure Storage account as an Azure resource, as a separate Azure resource, and the data we are using in workspace. So the data store here is the abstraction of the persistent solution or the storage solution we are using. At the end, this data store is interacting behind the scene with Azure storage. You have blob containers created, you have Azure file shares within this storage account. You fetch the data from there, from the blob containers, you push the data to the blob containers. These kind of interactions, it's already decoupled from your side. It's already abstracted by the data store. Once I have the data store in the workspace, I deal with the data store itself. I don't care about the underlying storage account. I'm just dealing directly with the data store itself. So that's all, which explaining the theory. Enough theory. Let's move on to exploring actually the different features in our machine learning service and in the workspace, as we said. Then After that, we are going to move to the demos. So let me share here my browser to jump into the Azure portal. So first of all, we are going to move on to Azure portal. As you can see, I have created here 2 resource groups. One resource group I have created from Azure portal directly, and another one I have created by Python SDK. Let me start from here, from this resource group, and to see what we have inside this resource group. This resource group has machine learning workspace. If you can see, this is the 3rd item here in the list. Let me increase here the size of the font just to make it very clear in the recording. We have here the machine learning workspace. And by default, when we created this machine learning workspace, automatically it created for us the application insights, the storage account, and the key vault, as we said. And this container registry has been created later because while I'm in the workspace, I start to train some models, and these models has been actually created Docker images, and those Docker images has been pushed here. So I have a Docker image here, and this Docker image has been actually created automatically for me while training my model, and also you can have a Docker image created after making an inference pipeline to generate predictions and so on. So this is a sample of a Docker image has been pushed, and because this was the first Docker image, this Docker image actually was created at the time I needed, because I didn't create the container registry while creating the workspace, as we explained before. And we have here something called container instance. This is Azure Container Instance, ACI, and I have it because I deploy some trained model. I already deployed some trained models that I'm going to show you after a while. And this ACI is actually something could be very suitable if you're still testing your model. So I want to generate predictions from my trained model, and I can see this actually in the test mode. Instead of deploying this to something like AKS, for example, Azure Kubernetes Service, I can simply deploy it to ACI as a best service and use it for testing purpose until I decide that I'm fine with the accuracy of my trained model. So let me navigate here to my workspace. This is my workspace. If you notice, this is actually has, from the left side, you can notice that I have 3 main sections. I have the authoring section, I have the assets section, I have the manage section. In the authoring section, we are concerned about designing the workflows or the pipelines for our machine learning. This kind of building the machine learning models, training the machine learning models, or creating pipelines could be done actually in either way. Could be done programmatically by using the SDK for Python, or could be done using the designer. Let me start with the designer, because this is the simplest part. If you open the designer here, you will find that you can create a new pipeline. You remember what is the definition of pipeline based on our introduction before. So if I open something here like car price prediction, this is one of the pipelines that I have created from the designer, okay? And because if you might know that the training of any experiment in the machine learning usually take from 20 minutes to 30 minutes for the small models. So actually, just to save time, I have prepared here some models to show you and train it as well, just to save time. If you can see here, I started from the raw data. I have a raw data, and this raw data is all about my data that I'm going to train my model on. And here, you can see this is your designer. And in the designer, you have a lot of things here in this toolbox, which is grouped by its purpose. We have the data set, which is all about the data. We have sample data set, which is some sample data set from the open data sets given to you, which you can use it actually for experimenting and for learning as well. And you have data input and data output, which is related to exporting data, importing data, enter data manually even. You have data transformation, which used in the data pre-processing or data preparation part. So I'm trying here actually to map the high-level picture of the typical machine learning workflow or the typical machine learning pipeline to what you see here in this designer, okay? Because this designer has been created to serve this typical workflow. And data transformation, as we said, it has a lot of things about the data pre-processing, the data transformation, how to reshape the data, how to add columns, how to add rows, how to apply some mathematical operations on the data, how to make some transformations on this data, how to even detect the missing data and cleanse it, clean this missing data or missing values, clear values, which is actually used for removing the outliers, converting to CSV, convert to data set, or convert to indicator values, which is all about something we call it in machine learning, converting the categorical variables into hot encoded values. The hot encoded values, for example, if I have gender, and this gender is male or female, machine learning models doesn't understand male and female. It understands only numbers. It's all about numerical calculations. That's why if it's a mathematical model and we actually try to feed numerical values to our model, we use convert to indicator values to hot encode the gender here. Instead of male and female, it will be split into two new variables, two new fields or two features, where if the specific record is a female, it could be 1, and if the other record is male, it will be 1. So you have, instead of gender, you have gender male and gender female as a new 2 columns, and in each column you have 0 or 1 based on if it matches the value for female or male. So this is a kind also of transformation or pre-processing we are doing in the data usually, and it's very common. We have also edit metadata where we actually mark specific fields as categorical features or numerical features, or just play with the metadata of the given columns in the raw data. We can make actually group for the data into bins to make it actually like ages. We have the age range from 20 to 30 and from 30 to 40 and so on. So this is a kind of grouping. So every person, for example, with the other attributes, his age will fall into this specific bin. It will be actually shown in the transformed data within this specific bin based on the setting we are doing here in the pre-processing part. We can make merge to the data, we can normalize the data. Instead of having very big values or inconsistency in the data itself, we can normalize the data to make sure that this data is actually within a specific range like 0 and 1, -1 to 1, and so on, because this is also has an impact later on in some specific machine learning algorithms to make sure that we are not getting bad performance during the training phase. We have like many things, but I'm going to focus on the common things. Like, for example, here we can split the data. This is a very common thing which we have already presented in the slides before. By splitting the data set into training data set and testing data set, we can use this split data actually to make this grouping of the data into training and testing with a specific percentage easily from the designer. And we have actually a lot of things here related to feature selections, the machine learning algorithms. If you go to the machine learning algorithms, you have regression. So this is actually the group of regression algorithms you can use here by default. It's already provided to you. You have a clustering algorithm. You have a classification algorithm. So it depends on the problem in hand. based on the problem you are trying to tackle here. So just for the sake of time, I will try to show you in action what we have here in this training pipeline. In this training pipeline, I'm feeding the raw data, then I'm selecting specific columns. So if you want to visualize this data, you can go ahead and visualize the data. So it's very handy that you can see the high-level view for your data. You can see that we have 205 rows and 206 columns. You can see what columns we have. You can see the histogram or the distribution of each variable. You can see also that the label or the outcome that we are trying to predict here is the price of the automobile or the car. So this is the price, and the other inputs representing the car features or the automobile feature, which will be provided to us as an input. And once our model is trained to map the different inputs and different features to this price, the final model could actually used to make predictions to a new cars. So in this step, we select columns. So I decided here, for example, to go and drop some columns or select some columns. I can add and exclude columns here. If you look here, you can see in this pane, you can see inside the canvas, it shows the different properties. Here, I selected specific columns in my data set. I said here, include all the columns in the data set and exclude only one of them called normalized losses. So I excluded this normalized losses, and this normalized losses, I believe it's not needed and it will not be added value during the training of my models. That's why I excluded from the data set. Once it's excluded, and if I look again to my data after that, I will be able to see that the data actually has all the previous features except the normalized losses feature. It has been dropped, if you notice, and I still have the other features. Moving on, we actually can see that from the data, we have many missing values, and these missing values, you can detect it from here. If you notice, when you click each variable, you can see here something called missing values. The missing values here for this one is 0. Missing values for this one is 0. For normalized loss, it's 41. And you can see in each one of them how many missing values we have. Why this is important? Because the missing values means you are feeding your model with data that might have actually a lot of null values or empty values, which is not a good practice. That's why I decided here to add in my pipeline another stage called clean missing data. I'm cleaning missing data across all the columns, and the rule I'm following here that despite any percentage you have as a missing data, remove the entire row if the entire row has a missing data. This is one of the way of thinking if this matches your problem or your data that you are trying to train your model on. However, it's your choice. You can play with this ratio, the minimum ratio of the missing values across the rows, or the missing values, maximum missing values. You can make it like 50% or something like that, 30%. So you can control the criteria, which is based on it, you will apply the cleansing for the missing values. For example, you might decide to, if the specific column the missing values exceed 70%, drop the whole column. Or if each row has more than 70% as a ratio with missing values, drop the whole row. Or may you decide to replace the missing values with the mean of this row, or the median of this row, or the median of the column. This is, or substitute it with something custom as a specific value you want to use to replace the existing missing values, or use mode. there are different settings. You can actually pick it from here, as you can see. So this is will come by experimenting, by having more knowledge, and you can, along the way, know what is the best choice and the best configuration for this cleaning missing data as a stage. Then once my data has been cleansed from the missing values, I have a split data stage, which we talk about now. I'm splitting my data here to training data, which will be 70%. This 0.7 is my 70% data, training data. And I'm randomizing the split, which means that actually I'm taking the split after randomizing the data to make sure that we are not actually having the same data coming with the same order. This is also a good practice. And I'm putting here a random seed, this random seed for reproducibility of the model. So instead of having, if with each run of the training, a different results, if we actually put the random seed with non-zero value, you will get the same exact result every time you run the same model. It will be reproducible results, and this is also a good practice to use. And this is the split. So what we expect as an output here, we expect that we are getting from this output point, we are getting the training data set as a 70% of the data, and we are getting 30% of the data as a test. So this branch is the training, and this branch is the test. We actually here train the model in more complicated way by picking logistic regression algorithm, linear regression algorithm, because this is a regression problem. We are, if you remember, we said the regression problem, we are expecting or predicting or make the mapping against the continuous or real-time number, which is the price. In this case, it's not a discrete value. It's not specific outcomes like 1, 2, 3. No, it could be any real number. It's a continuous value. So we use here one algorithm called linear regression. And this linear regression actually also has some configurations here. We can use it. We have also here the train model module, and the train model is expecting two inputs. What is the algorithm that we use to train our model? And what is the data, the training data? If you remember, this is the 70% of the raw data that we are going to train our model on. So we are running the training here, train the model. Finally, we get from here the trained model. And this trained model, eventually, we need to score it. Score it means to make validation and make sure that this final trained model can act well against the test or the unseen data. So we have here in the score model, one input for the trained model and another input for the training data set. This training data set, which is representing the 30% as per our configuration of the raw data or of the given data. And finally, we get the scored data set. The scored data set, which is actually the prediction. What kind of prediction we get from this model. And this scored data set will be entered here in the evaluate model. Evaluate model is making the assessment of the model based on the prediction by comparing the predicted scores against the actual scores. Because if you remember here, we have already the prices from the test data. It already has the prices, but the difference here that our model didn't see it during the training. It will see it only during the scoring and evaluation. So the evaluate model, based on the comparison between the actual, the prediction given by the trained model and the actual numbers given by the test data, the evaluate model will be able to give us the accuracy of this model. And we can see here that this is the accuracy metric or the evaluation metrics that we get, because this is a regression problem. That's why it's giving us, for example, mean absolute error. This is one metric. We can compare our prediction against the actual value. And this is all about direct subtraction between both and taking the absolute value to make it always positive. And here we have the root mean square error, which means that you are subtracting the predicted score from the actual prediction and eventually take the root square root and actually take the square of these numbers and finally take the root square of these numbers. So you have here the mean squared error. So this error itself is squared, and we finally we get the root mean square error to assess how much difference between, in general, as an average, as a mean, between the expected values, the predicted values, and the actual values. If you notice here, just to be very concrete, with the measure of the mean absolute error, we have 1,829. This is the mean absolute error across all the test data. And we have this number as a difference, as an average difference between the actual numbers, actual prices, and the predicted prices. And with the measure of the root mean square error, we have this number 2,500 as a difference between the actual price and the predicted price, which is pretty nice because at the end this is a car price and we have this difference like 1,000 plus or so. This could be accepted, and we might also decide to go and train our model again after doing some changes in the parameters or selecting another algorithm to get more better results in the prediction. So this is how we can see the results, okay? And here in the right side, I also trained my model in another regression algorithm called boosted decision tree regression. I'm training the model. I'm scoring the same model against the test data, and finally I can see the scored data set and give it here to the evaluation model. So this is also a way within the same actually pipeline to make assessment between both. If you notice here, we have two numbers. Each row, we have two rows, and each row has these kind of evaluation metrics we talked about. The first row is representing the linear regression, which is the left side. The second row is representing the error or the difference we get from the boosted regression model, boosted decision tree regressor, okay? And this one, decision tree regressor. And you can compare which one is better. Yani we have the linear regression against the boosted decision tree regressor. These are two different algorithms, and you can see in a clear manner that the first one is better because we have less error. So it works that the typical linear regression algorithm will do well in this case because it's actually minimizing the loss, minimizing the error. You see here this 1,800 plus. This is 2,129. This is 2,500. This is 3,010. So it's obvious that the linear regression algorithm, for example, is doing great in terms of minimizing the error in the prediction. Okay. So this is the main idea here, and by that we explored all the stages within the pipeline. But actually, keep in mind that this is not the only way you can design your machine learning solutions. You can also use the notebooks. This notebooks is a great way actually to programmatically do a lot of things which you can do it from the code instead of doing this from the designer. So if I switch here, and by the way, even you can do this from your local machine against the machine learning workspace in Azure without even hosting anything initially in Azure, but just interaction based on the SDK and based on the code to create and manage the machine learning workspace to train your model against a specific compute target. And if we go back here again, we can see also that, just to make sure that I explored a lot of things, here we have the experiments I have run. This is different experiments I have run. If you notice, each experiment here has multiple runs, multiple trials, as we said, because we defined the experiment as a collection of multiple runs. I make updates on my pipeline that we have just explored, and I keep submitting the run, and each run actually will be listed here under this specific experiment, because all the time when I'm executing my pipeline, it will be executed within the boundary of an experiment. And also it will be served by a specific compute. That's why we have the compute here. And if you notice here, this is a compute instance and this is a compute clusters. This compute clusters where we can actually create a new cluster that we can use it for training. Just if you allow me, I will connect my charger because I can see that it's about to disconnect. So a few seconds, please.
Anyway, in the meanwhile, if anyone has any question, you can just put it on the Q&A section. And Osama, I think, how long is still remaining? And how much is remaining?
I think we take already. We are after the specific time slot specified for this session. However, I have a lot of things to discuss. If you would like, I can just make a quick overview over the compute part and just give a small hints about how to do the same thing programmatically as a high-level overview. Maybe 5 or 10 minutes more should be for this. Okay, so let me
go ahead.
Yeah. By the way, Tariq, do you have any questions so far? If you are following
No, we just had some, actually, it's not a question, it's a note from Asil. Asil was asking that, she's saying that thank you for the valuable information and session, but she's asking for such, session, but to be in Arabic. So, يعني أنا هحكي لأسيل أنا جاوبتها. I will switch in Arabic to answer. أسيل إن شاء الله هيكون في ورشات زي هيك باللغة العربية إن شاء الله. وخيار الترجمة already مفعل. I just also mentioned that the video is already contains some automatic subtitle, and Arabic is one of the languages supported. We know it's not 100% accurate since it's an automatic what you call it, subtitle, and it's based on some of the machine learning for sure, yani, which Osama is presenting. Yani, we are relying on one of the Azure services called the speech service. So, but inshallah, in future, we'll take this in consideration. Maybe we'll start also providing some Arabic sessions. Mic to you, Osama.
I think, let me answer in Arabic. أسيليو يعني أنا متفق معاكي إن the same sessions يعني should be conducted in Arabic. Sometimes يعني المصطلحات بيبقى الترانسليشن بتاعها مش سهل، ولكن اتليست الدسكشن نفسها لو بالعربي ممكن تسهل على ناس كتير المتابعة، وإن هم ممكن يستفيدوا أكتر من السيشنز خاصة في المنطقة العربية. إن شاء الله نحاول نعمل ده في المستقبل القريب، ويبقى عندنا Arabic sessions يعني بحيث إن نقدر إن إحنا يعني اكتر عدد من الناس يقدر يجوين معانا بدون اي صعوبات ان شاء الله. تمام. ده بالنسبه لموضوع الارابيك سيشن يعني. If you allow me, Tariq, I will go back again just for 10 minutes more to finish.
Sure. Go ahead.
Because really I have many more demos to explore and to explain today, even from programmatic point of view. However, I would like to show you some interesting things here about the predictions. You remember this this pipeline that we explored together for the car price prediction. I have another one for diabetes to expect based on the specific inputs of this person has diabetes or not. And this actually I have trained based on a data set from Kaggle. This is actually I get it from Kaggle. Kaggle is very famous website where you can join the community to learn data science and machine learning, and even they have competitions where you can participate, and they have also courses and notebooks which you can learn from. So I downloaded this Prima Indians diabetes database, which has specific inputs, and the output here is either this person is diabetic or not. So it's a binary classification problem. And if you notice, this is a pipeline I have created for this diabetes problem. And I have registered this database here, dataset here, as a registered dataset. And more further, this dataset, once it's registered, I can profile it. I can actually make a statistical summary on this data. I can explore the data. I can generate a profile for this data to see the statistical features of it. And what it means to have this data set as registered in general, it's registered within the workspace, within the machine learning workspace. So the advantage here that will be shared across all the experiments within workspace. You might have hundreds of experiments running within your the same machine learning workspace. So once you register a specific data set, this data set will be actually available across the whole workspace, so you can use it everywhere within this workspace. And also, we have here the models. I have one model, two models actually, I have registered. What it means to register a model also, same idea, that once you have a registered model, actually you have two advantages. The first advantage is that you are saving the final outcome of the training pipeline. So you can use this artifact, the model itself, later in the predictions. And you can take this model, you can download it in your machine. You can use it actually as a portable format to be used for the predictions in a specific system. Or even further, you can actually deploy it in Azure, Kubernetes cluster, or in Azure container instance. It depends on your needs to as an endpoint and start serving prediction from this model. I have an example here for one model, and by the way, this is giving you a very nice feature to version your model. If I'm trying to enhance my model over time, and I have new versions of the same model, if you notice here, I have version, and this version automatically will be incremented if I'm actually trying to create a new version of the same model based on the name. So if you notice here, from the same experiment, I can actually create a new version of the same model. And with that, we will have a history or a version control of the models, which will be a very nice thing if you have a lot of work in data science. And I also deployed one of the models here, which is the car price predictor, as an endpoint, as a REST API web service. Let's see how it will show us some predictions. If you notice here, I have a tab for test. And I have deployed this on the compute type of ACI, Azure Container Instance. And in the test, it's giving me sample input for the web service. And it gives me also what is the actual price. This is the actual price. Just to make sure that we can compare between the actual price and what is the price we will get from the model when we ask for a prediction. So I'm going to hit the button here to test. And eventually we get the test result. This is the prediction that our model predicted, which is the scored label. This is the scored label, is the predicted price. If you compare between the actual price against the scored label, which is the predicted price, you can notice it's very near. The error here, or the difference, is very less, and it's very small actually compared to car prices. And with that, we can recognize that the accuracy of our model is pretty good. Okay. And same idea here, I can consume as a developer. As we said before, we can consume this REST API from client applications. So I have here C# sample for this endpoint. I have here Python if you are a Python guy. I have here R if you are coming from R programming statistical background. Okay. Especially for people who are working as statisticians. And you can also simply take this endpoint and go to Postman and just put it there to get the same result using the primary tokens or the secondary keys in your authorization header in Postman. I will show you a sample here for Python. I will copy this one, okay, because it's coming with all the parameter values we need, like the endpoint URL, like the keys, and so on. And I'm going to switch here. I'm not sure if this is shown to you or not, but let me share it just to make sure that you can see this, so you can see what predictions we'll get. Here, I'm going to create under demo 2 a new file. I'm going to create this file. I just paste what I have. If you notice, there is a request payload, which is representing what data will be actually passed to the prediction endpoint, and the URL of this endpoint. It's a score endpoint to score and to predict, and this is the key. Okay, with some headers for sure. I'm going to save this file as I will call it inference.py. Okay. So this actually I have it now as Python file, for example. So this is the infer.py, and if I switch it here, let me switch to my terminal. Okay. I have my terminal here. Not this one, the other one, sorry. Just to show you how to do this as for people who are coming from development background. I think you can see the terminal now, okay? If I just switch to demo 2, because I think this is in demo 2. Yeah, and this file for Python, we just call it here, okay? UI, okay, simple as that. And finally, we get the response. I hope that this is the font size is clear. If you notice here, I will be concerned only about what? About the label against the actual price. So this is the same scored label, which is the predicted price for the car with these attributes or these features. So it's also the same. And if I switch it finally here to my Postman, you can see the same in Postman. I know this will be something good for anyone who is working as a developer, okay? So that's why I'm showing it. I created here the body. I have the body for the payload, and I have the endpoint, I have the authorization header, and finally I hit against the endpoint, and immediately I get the result, same result. So this is actually clarify the different scenarios, and starting from the training until converting our trained model into a registered model in the workspace for the later use and for the versioning, for making this registered model shared across the whole workspace, and finally converting this model into an endpoint which can be consumed by different clients, different client applications. The last thing that I'm closing with is about the compute, because this is also important. So let me go back to the workspace, because I believe for the Python SDK, we need another session. I have a lot of nice and exciting things about Python SDK, which I already prepared, but it looks to me that there is no time to discuss it today because we already ran out of time. Under the compute, you can see here that I have a compute instance. What is compute instance? This is actually the compute. It's finally a VM, virtual machine, that we are provisioned under the umbrella of the machine learning workspace and it will be the underlying compute for the Jupyter notebooks. You remember these Jupyter notebooks? These Jupyter notebooks, where it's running in some virtual machine, somewhere in a virtual machine. And actually, to make sure that we are able to execute whatever things and stages related to the machine learning within the Jupyter notebook, we have to create or provision a compute instance for that purpose, which is finally will be here in my example. It's a single node I created to serve as a compute target for the Jupyter notebook. I have also the compute cluster. This compute cluster will be used by the pipeline. If you notice here in the designer, we have here this one is already attached. This pipeline is already attached to this compute target that I have provisioned before. I have two compute targets here, compute clusters here. One with a single node, another one with two nodes. And the nice thing here to notice about the compute targets, it's very optimized and it's already supporting scalability, auto scalability by default. What does it mean? It means that simply, by default, you have two nodes in your cluster for training. You are not training anything now. Your pipelines are actually idle and you didn't start anything. So even with your compute cluster provisioned, it will be zero node. No nodes will be active until you submit your pipeline. Once your pipeline is submitted, the cluster nodes will wake up, and after a little warming up for these nodes, it will start actually gradually with one single node and scale automatically to the second node, third node, depends how many nodes you have, based on the need, because at the end you are running parallel tasks, and those parallel tasks will be executed in across the different nodes within your cluster. And if you don't have a need for auto scale to more number of nodes, it will not actually scale. Otherwise, you have this auto scale as a feature, so it's very handy. Eventually, after your submission or your experiment run is done, and you have done the work you are doing in the machine learning workspace or in a pipeline, automatically this training cluster will shrink down to zero. So you are not going to incur any cost if actually you are not executing any kind of pipelines or executing any code in your Jupyter notebooks. So this is about the compute cluster. And also we have something called Inference Cluster. This Inference Cluster, from its name, this is the clusters we are creating to serve predictions. After we have the final model, we want to serve the prediction. We want to deploy this model to AKS or ACI. This is where we are creating the inference cluster that we can use for that purpose. So there is a clear segregation here between the training compute clusters and the inference cluster to have a good management of it within the workspace. And also, eventually, you can also attach external compute. I have a VM. I can attach this external VM that I have created manually to my workspace. I can also attach Databricks, HD Insight, Hadoop cluster, anything that I have created and I wish to attach as an additional compute to this workspace, also I can do it from here. So this is like bring your own compute. This is the idea of the attached compute. So I think this is enough for today because I believe there is too much to explain here. And as I said, I have also some nice things related to the developers about the SDK, which could be in another session, as we said, which is actually how to see the same idea of the machine learning pipeline, but from a code perspective, and how to run the same pipeline programmatically from start to end, from the training phase, and eventually have your trained model registered automatically from here. By the way, I'm running this from my local machine, and I'm hitting another machine learning workspace in Azure, and I'm 100% controlling every single aspect from within this Jupyter notebook that I have created in my own machine. So that's all for today, and thanks a lot for joining us, and thanks for having you today.